Carolyn, for joining us. I was fortunate to meet you and, what was it, 2 years ago, and a project that we're involved with looking at food and urbanization, trying to understand how the shift towards urban populations worldwide affects food biodiversity. And I bring that up because it's kind of an indication of the breadth of work that Carolyn is involved with. Her PhD is in geography, but also in social data analytics. And so she looks at a whole range of types of data about different things that people do. I'm just looking at my screen about a preprint that you have looking at pollution, air pollution associated with the COVID shutdown. And so I'm interested in reading that. But she does a great range of work using kind of big data and geospatial analytics. So I think we're really lucky to host her sort of in the department, virtually. And I'm also excited to say that she's taken a job at University of Canterbury in New Zealand. So she'll be starting next summer as a tenure track faculty there. So please join me in welcoming Dr. Carolynne Hultquist to our colloquium series.
Thank you. I can see the applause. Yeah, it's great to be here and talk with you all. And I'm actually going to be talking primarily about the work that I did at Penn State for my dissertation. So I thought that would be the best to highlight on the screen. And then at the end, if we have time, I might also discuss about how this is leading into some current research that I have ongoing at CSUN, which is at Columbia University, of incorporating other types of data related to population and really looking at not just exposure, but also vulnerability. So really going to focus on talking about from the sky to the crowd and focus on remote sensing and citizen science approaches within decision-making for hazards. And then we'll see where we get from there. I've heard that I should probably go about 40 minutes or so, and then it's like open for discussion. And so we can cover some other topics then too. So I'm gonna see, there we go. So this is just me and like a word cloud. So I cover many different topics. I'm very interested particularly in validation, and that's what I'm going to be talking a lot about today. And validation of crowdsourced citizen science data set, but it kind of fits into this bigger framing that I have of looking at information in a system. So I am a geographer, and I consider myself a spatial data scientist, and I cover a number of things with disasters and then increasingly with food security topics, including some AI related projects that are starting up on those in that area. And using a number of different types of geospatial methodologies, and really within this context of a system. And so I hope that's kind of like the picture that you get from this is that can be applied to any type of research application or area, not just within a hazard setting, but to any type of work. As you said, I've got geography and social data analytics background. And so I try to incorporate these from like a data analytics perspective and a spatial side, and try to bring together both of those areas when thinking about these problems. So overall, like the real focus that I have is on incorporating or this integration of data sets. And really the focus that I've had is on thinking about situational awareness. So for a decision maker, what sort of information do they need about hazards, and how can we incorporate different data sets to try to get that situational awareness? This could also be thought of as like geospatial intelligence or geoint kind of focus, I guess. And in this process, I started to see that beyond just traditional remote sensing sources, a lot of times there's a need for localized sensing. And it can be for different conditions that are not able to be detected from remote sensing instruments. And sometimes it can also just be about the resolution of that information. So we might not be able to actually identify things as deeply as we need to. And so I think this is where a lot of crowdsourcing data sets can come in, of trying to fill this gap, of where you might have it at a certain time period that you need. There might be conditions that are keeping you from being able to detect or to recognize a hazard in that space. So I first actually started with using social media, and I started to combine remote sensing and social media a few years ago, and looking at if there's ways that we can look at, let's say, the quantity of people that are talking about power outages in social media, and combine it with what we actually observe from like nightlight imagery of where there are power outages. And I started thinking about this role of having areas where there's more people, let's say within the study area of that have power outages, that are talking about having power outages, than people outside of it, and kind of like some of these spatial relationships. But I also started recognizing that in social media, we have this like really big like data mining kind of aspect, where it's hard to detect sometimes if people are trying to say that or trying to express that information, and it's hard to determine kind of what it's capturing, because there can be so much other noise that's involved in social media content. And so I started thinking about what type of projects or what type of crowd-based things are actually intentional. And that's how I got into citizen science approach directly, is that it's not just something that you're scraping or something that you're pulling from general content, but people are intentionally trying to give this information. And a lot of times they have a specific objective in providing information in that space. And so I started thinking about this integration of these many types of heterogeneous sources, kind of in this way, of this systems approach, in which you have sensor networks and models, airborne collection, a lot of our traditional sensing sources, and these contributed sources such as citizen science, other crowdsourced projects, and social media, and how they relate. So at certain time periods within, let's say, a flood event, we might be able to have remote sensing observations, but during, let's say, a hurricane, you might not be able to get a clear image from optical of that event. It might be way later by the time you're actually able to pick up another image based on the temporal resolution of the sensors. And I mean, increasingly, we also are having SAR and some other products that are able to do that, but they're not very high temporal resolution, so we don't have consistent images. So the idea is to try to fill these gaps temporally with information from other sources. And so I started looking at events and seeing if I could capture citizen science observations at different time frames, or UAV, which are often at the end of a hurricane, after the intense wind, and that kind of thing, because you really can't fly it during it. And I started thinking about this kind of temporal nature of how we can put together the pieces of these different sources in order to kind of have a more collective picture and a trend of, let's say, flooding throughout the cycle, as opposed to just snapshots. And so from the sky, let's say, from the remote sensing kind of perspective, there are so many more platforms that are available today, and a lot of which are openly available. You can also, through research agreements, get access to a number of different sources. Like for small satellite, Planet has like a research agreement. Of course, all the USGS sort of sources from Landsat. And there's partnerships that you can get to try to get more or get access to other types of platforms. And there's just so many free sources available too, and starting up from other countries beyond the United States, like the European Space Agency with Sentinel, the Japanese products. And there's a number of different things available just in the last couple of years that we can use. And their functionality is beyond just optical too. So we have a lot of SAR-based sensors that are able to get flooding, let's say, below vegetation, or better in urban areas than they used to, and algorithms are being developed for that. So there's some really promising new directions in this space. A lot of areas also have UAVs. So like I started picking up UAV feeds from YouTube. People would post of flooding after, like right after the event, or do it even live feed. And so you can start picking up these sources over time. And in a way, it is kind of the crowd too from those sources, because it's UAV on YouTube. So I guess it depends which category you want to put that in. And then along with this push of the crowd, which is really just, there's so much abundant data now from citizens that are both unintentionally collected, as we discussed, like with social media, and intentionally collecting for a specific, let's say, environmental monitoring purpose that can be used during disasters. And so for my dissertation, I really focused in on this public involvement and this intentional collection of observations. And despite this, people might have an unknown level of expertise, but when I started working with a lot of these groups, I started realizing they did have a lot of expertise in certain areas, and people develop expertise in these areas over time by working on these projects. And so that's something to keep in mind. And so this data, right, it can be integrated with the crowd to satellites, and this integration does have different levels of uncertainty that you have to think about with how the data were collected, going into the standards and the documentation of each of the data set, and seeing how you can align the data sets in a way that's meaningful and representative of what the data was collected on. And so this fitness for use question, I think, is really important to consider. And so this kind of guided me to look at a project. I started looking at the SafeCast project, which to date now has 150 million observations of radiation levels. This is the Geiger counter device that they developed. And this is their web-based map of radiation levels in Japan, which are mostly along roads, and actually kind of the interpolated, kind of like paled out area in this map is what they kind of just interpolated, linear interpolation over space. But their data is really actually in the kind of more standing out blue colors there. But it was a crowd-funded project with sensors built from off-the-shelf parts, except for the sensor itself, like the actual detector itself. And it's an open project with contributions from all around the globe now. But most of this data is collected right where people live. It's in areas of human activity. It's not a broad survey. And so when I started to look at this, like zooming in a bit, this is like their interpolation of it. This is the Fukushima area, and we're going to be kind of zooming in on this. Actually, can you all see my cursor? Or I'm not sure. Yeah, you can. Okay. So this is like where the reactor is. The Fukushima disaster that happened in March 2011. And there was a release of radiation to the northwest. And this is their interpolation that they show online of that radiation. And I started looking more deeply at this and just kind of think of this as a, I don't know, like a kidney bean for right now, the shape that's being extracted. This is a zoom, like the same area. And so this is the SafeCast data on the right-hand side that was collected in that area, but it's mostly along roadways and like in the Fukushima city area and some other towns and towns along the coast. And they actually don't have a lot of data in this area of high radiation, which is actually a good thing because it means there's not a lot of people exposed to it. But the point of this is, like, if you just compare the raw data to, let's say, a survey, which was an airborne survey taken by helicopter and airplanes from the Department of Energy and Nuclear Agency. They basically took swaths of airborne radiation levels, and they get this broad picture of radiation over the area. And when you look at the statistical profile of the data set on the left compared to the one on the right, it's very different because they're collecting in different areas and they have different quantities of high levels of data, right, collected in different places. And so direct comparison of this just didn't work out if you're just looking at it statistically. So I really wanted to look at it spatially. And so I started realizing that there's a lot of uncertainty even within the SafeCast data set itself. So this is a Bayesian kriging of the data, the SafeCast data. And basically, this is counts per minute. It's a radiation unit. So low radiation throughout it. So this is the probability that you would have greater than 100 counts per minute in this area. And as we continue to get to higher levels, we see that there is a grouping here, 600 counts per minute, which is a really high level of radiation that is mostly within the main plume of the radiation. So the extreme values are falling in the right place. But there's also a lot of gaps where they don't have data. And it wasn't exactly clear from what their metadata and standards that they provided, how they were dealing with that, how they were interpolating, what sort of methods they were using for their maps. And so I had conversations with them and started to engage with them about how we can try to capture that data or capture that uncertainty. And so what I did was I accessed this data from the Department of Energy, the SafeCast data, and 2 other background surveys and a deposition survey from after the event. And I spatially clipped it to the same area and within the same half-kilometer grid cells. And I was able to remove the background levels because of this survey done by the Japanese government in 2007. And I decayed the data, since it had been collected at different times, to the same time frame based on our physics understanding of how radiation decays. And I was able to basically create data sets that were essentially at the same place and time to actually do a comparison between both of the data sets. And so I clipped it down to grids that we actually have data from the Department of Energy and from the SafeCast data, and was able to do comparisons statistically between them and found that they were over 90% correlated, which the government people were surprised about, that the citizen science data was so aligned with their data sets. And the citizen science people were also surprised that the government data aligned. And so there was an agreement there, which was actually a really good thing and led to some valuable partnerships between them. And the idea is that then we get to this point after we've integrated the data where we might want to disseminate it and show different levels of uncertainty, show where there is potential error, and lead about kind of this discussion where we can have representation of that as opposed to just a plain map of levels, but actually some representation of uncertainty in those spaces. So this led, this kind of came to some other areas where I started looking at from a modeling space. And so this is a modeling of it. So instead of just the 2 data sets, I started looking at modeling the distribution. So this is a Lagrangian particle dispersion model that's run here. And this is the source that we give it of how much emissions there were. But for the most part, the wind was blowing out over the ocean, and so it wasn't on land. But for a short time period, which corresponds right there with the graph where we have this red line of the land concentration, it was over land. And that's what this leads to, is this kind of swath here where we have radiation from the northwest of the reactor, but also that went down along the mountain range, and we have some higher concentrations here too in the mountains. And so this leads to, because of this model, we're able to calculate with the terrain and the precipitation and other sort of effects, like the actual concentrations on the land, which is different than what the classical model is, which is just a single direction. It's limited because it only, the Gaussian model only has, is only able to function as being dispersing in one direction, whereas this high split model is able to pick up that distribution as shifting from the northwest to the southeast, and it aligns really, really closely with the Department of Energy and the SafeCast data, which shows higher values than baseline, the natural radiation in the same spaces. So this ended up like being a very good demonstration of how you can combine different models and 2 different data sets and confirm similar areas as being high radiation, and including in populated areas. And this was another way that I kind of approached it, was looking at taking these cross sections. So across, let's say line 1 here and 2 and 3 correspond to these graphs here, 1, 2, and 3. And we're able to compare between each of the models and each of these data sets and find similarities between them as being peaking in the same places and having higher levels of radiation within the plume. And also picked up some other peaks that hadn't originally been identified by the Gaussian model, which I should say is the traditional model that's used when there's an event. And it's also the model that's used when you're putting in a nuclear power plant and putting in preparations for things. They use just a direct Gaussian model and don't consider the meteorological or terrain implications of the spread of radiation. So I thought this is an important piece of adding this model to consider the distribution. So this, I should mention, this is the line going lengthwise down the middle of the plume. And you can see the comparison here of integrating with each of these data sets. With the red line, the Gaussian model just has a simple solution here, whereas the high split model, the blue line, the Department of Energy, the black line, and the SafeCast data pick up these higher levels of radiation around the same places. And so I think that's useful to consider that they're able to all identify the same spatial patterns of radiation in those areas. And you can also identify when one doesn't pick up something and why. So if the SafeCast data doesn't pick up a point because there's no roads or population there, or the high split model has an error. So you can kind of adjust for that because we have multiple different data sets that we're integrating. And so I think that's a useful feature or aspect of this methodology. So the kind of bottom line that I get to here is the importance of understanding the spatial scale, because nearby locations could have different results. And that's very common with sort of certain types of environmental monitoring, where the spatial distribution could be very different if you go up the mountain slightly, if you look into areas that have higher radiation just nearby, or forested areas or things like that. There can be these microcosms, maybe you could look at it, of differences in radiation that we should think about and consider. And having a perspective of crowdsourcing enables people to provide their own observations, whether it's localized monitoring or indoor spaces, let's say for air quality, which can be very different for indoor versus outdoor spaces. And I think crowdsourced data can really help to make us think about and evaluate these different levels of environmental contaminants or pollution or issues over space. And I think that's an important aspect of this. And we can think about the inconsistencies within the modeling or different measurements by aligning these data sets. So this is another project that I wanted to just discuss. And this is kind of built on the same concept, right, of integrating these different data sets through this process. And this is for flooding. And so I took some crowdsourced observations, which were pictures that people took of flooding. And I combined it with USGS data of both stream gauges and high water marks. Stream gauges are generally available pretty much in real time, but as we're going to see, they're in different locations than what we might need because they're right along the streams. And the high watermark data can actually be really useful to actually looking at the extent of flooding and how much human impact there was in these spaces. And then I also used a model from Pacific Northwest National Lab called the RIFT model. And it has especially depth from these inputs, which was essential to look at to compare between the measurements. And then remote sensing imagery from SAR. And I didn't have the depth specifically here from the remote sensing imagery. So the comparison here that you actually see is the percent flooded for that area, which I realize is not the same thing. But the main interest here was looking at trends and seeing if areas that have higher depth should be, right, on average flooded more. The percent of it should be flooded more because it's deeper. But we understand that, take that with a grain of salt. So first off, the crowdsourced ones were integrated in, and we used it to compare between these and detect different patterns from these standardized rasters just in general. And then we looked at finer grained through cross sections to see where the measurements aligned in similar places. The red dots here are the remote sensing, SAR based, and we'll cover more of this in a minute, but these are the integrated, or the comparison of the cross sections. And then we integrated through comparing these different sources and augmenting, I would say, the traditional sources with crowdsourced observations. And so this we can see is just an overview. This is from Hurricane Florence, the event that I chose to focus on. And most of these crowdsourced observations of flooding are along roadways and in populated areas in towns. And the rift model here shows areas where they are flooded. I know this is kind of a zoomed out view right now. So this is a bit more zoomed in. So this is New Bern, and you can see that there's an urban area here. You can actually kind of see here from the street layer that there's a number of stores and things in this area, and this is zoomed in from this portion here. And we have the rift model, which shows us the flooding, but it's mostly guided by these gauge data from USGS, these green circles here, which is showing the depth of the flooding in these areas. And while they do have one or two, it looks like two different sensors here in around the town, they don't actually capture like the full flooding within the urban area and all the areas that are actually flooded, because the gauges don't reach that far. There's not the extent of the collection. And we'll have another example here. This is Boiling Springs Lake. It's a town, and we have the flood from the rift model here. And the USGS is showing that there's a lot of flooding in this area through the green circles, and the black circles are the crowdsourced data. And they are often along the roads, as you can see, and like in these populated areas, which while they are capturing some of the same things, like let's say here with the model showing along the road, there's other areas where they capture that are not captured by the USGS data set because it's not in that space. And so I guess I think of the citizen science of these crowdsourced observations as contributing a lot of times in urban areas or in spaces that are along roads that might not be captured by the other data sets. And so the bottom line here is that I would say these contributed data in some cases, particularly with these crowdsourced observations as opposed to the USGS high watermarks, they can be more timely than the traditional inputs. And likewise with SAR, it can often take like a full day. I mean, good to be really good would be like 10 hours maybe to get a flood extent from, let's say, the ARIA JPL kind of outputs of flooding. And that's much, later than the event, and it's not as timely as, say, as someone taking a picture. And if we can harness that of people's pictures instantly being captured by these kind of projects, I think we could do a lot with them for monitoring and responding to hazards in more real time, as opposed to like a post-assessment. And I think also the bottom line here is that the measurements do align with the traditional. So when we do have the comparable data, we can actually see that their measurements in the same places and times are similar. And likewise, that there are certain places that might be covered by one and not the other. But if we're actually looking at validation, we should be focusing on when they're both in the same place and time. And we do need to ask about this question of completeness. Like, I wouldn't say that we should only use crowdsourced data. Like, that's not the point here. The point here is to try to augment it. And particularly that it can be directly relevant to these human impacts, and particularly in urban environments and where people are, that we can provide information on those spaces that might not otherwise be captured through the more traditional means. Now, there is this question ongoing about how to ensure that we have contributions. And you can put in static sensors, but as in the case of any sort of monitoring, like they're at risk of damage and you might not choose the right places. So some people have suggested for citizen science that we just put in a lot of sensors, and we could put in a lot of low-cost sensors. But many other projects can do that too, or many other organizations can do that too. And I feel like the real value of the citizen science aim is not necessarily towards that. A lot of times it's being able to be dynamic and being able to incorporate things like images and other things that might not be a traditional means of collection. One thing though that I do want to discuss, and I'm open to talking about this further in the questions too, is this ethical aspect. And I've discussed this some with different citizen science groups about what about the potential harm to volunteers. I mean, when we have a academic or an organizational thing, we have IRB reviews and things like that, and we have to think about the ethics of having volunteers engaged or potentially in hazardous areas, potentially even seeking out hazardous areas. And how do you ensure that you make sure that your volunteers know that they're not supposed to go into the middle of a flooded area in order to get an observation, or that, you know, they shouldn't seek out areas with high radiation levels. And I think these are like really important questions to consider and think about. And I think it also shows a need for more partnerships between academic institutions and organizations that are thinking about these ethical considerations, and people working with these groups, these crowdsourced groups. So I think these partnerships are really apt, and it can help from data and standards to these ethical issues and so many other things by having these kind of partnerships. And it might not be something that's directed by a academic or a institution, but it could be something that's more of a helping those groups that I think could be still keep the unique character of each of these organizations, which is often very different than academic research, while not, but also helping them. And so I guess my bottom line is that it can be a benefit in the context of decision making. We just need to be aware of these different constraints, and we need to think about the ethical and evaluate some of these issues that might arise when we're using these data sets. And so kind of future directions of where I'm planning to work on with this is using data from the crowd to improve the resolution of the models themselves. So using it as inputs, because certain gauge data and things might not be working to be able to get the full extent of the flooding. And I think it can be a really useful input to help improve the models themselves. And then I also am interested in connecting across the temporal space for the disaster cycle, and trying to think about what data sets we need to use in each particular stage, and maybe kind of trying to find like a guideline for that of, okay, which type of data set should you be looking for? Where can you access them? What can you do? Because there is a lot of, I guess, like there's a learning curve to start accessing and using these data sets. And I think it can also be used as an educational tool to get students involved with these projects. And then the last thing, which is actually what I've been working on mostly now, is coupling this flood exposure and these model outputs with vulnerability and with populations in these areas, which is something that Season, my employer, focuses a lot on. And so trying to incorporate not just the vulnerability or just the flood model by itself, but trying to link them together and incorporate how we might plan for flood risk, let's say in a specific area or specific region, and what are the underlying vulnerabilities in that space, and therefore how it can inform our actions, let's say as a humanitarian organization in that space, to have information about where people are and their exposure to hazards, particularly over different seasons and different timeframes. So that's currently what I'm doing, and I would be glad to take any questions on that or any of the other topics that we raised. So I might stop the sharing for now. And then,
Thank you, Carolyn, for that
yeah.
fascinating presentation. I know there's going to be a lot of questions here, so I'm going to suggest to everyone, you're getting lots of clapping. I'll clap too. I'm going to ask the people, why don't you type questions into the chat, and then I'll read them to Carolyn, but then if you have a follow-up, you can unmute and ask your follow-up. All right. I have right now one compliment in the chat from Dan Dugas, just saying thanks for what you're doing. It's amazing and important research, and some clapping in the chat. Any questions for the chat? I know my students from our afternoon class have some thoughts about this from our earlier discussion. Yeah, Chris Duval.
Can I just ask rather than typing it out?
Yes, you can.
Thanks, Carolyn. It was great to learn that about that aspect of your research. I'm curious about the institutional aspects, like you worked in Japan as well as in the United States. You'll presumably do some work in New Zealand. How does it differ, because you have such different institutions with data collection and data sharing? You know, that's like the non-crowdsourced portion of it. How does that affect the capacities of you or people doing similar research to apply crowdsourced data to kind of understand these natural hazards you're looking at?
Yeah, I mean, I think there definitely is a lot of variance based on country, based on the certain areas. And it's something to think about also in relationship to vulnerability. The most vulnerable people might not be contributing to these projects or might not be creating these projects. It might be something that through partnerships and that sort of thing, you could provide access to different areas. I've worked on some projects now in Latin America and Africa, where it's text-based contributions, for example, because most people don't have smartphones. And it's something that I think you need to think about when you're designing the project, if you're an academic or an organization that's implementing it. But as you said, it can also influence who's actually creating these. And most of the projects I focused on are ones that have kind of organically sprouted. And they are based on having the technologies and having access to data storage, data management, and those kind of processes, a lot of times with web-based applications and things like that. And you're right, there is a lot involved with that to be able to have that capacity already. But I think we're seeing increasingly more of that throughout the world, where people are developing these skills and capabilities, even within a business setting or data analytics setting, where people are able to put together these data sets and share them. And it's something that I think will continue to grow. I mean, and even the capabilities of them will continue, because like the SafeCast project started off in a lot of ways as a pretty small project. It was just a group of a couple people, electrical engineer, computer guy, and they got together and put this together, but it's now developed into a huge network. So I think the capacity can develop over time. So it looks like we're getting a lot of questions. So I should probably
let me jump to the second one, because it's about the thing you were just finishing with on the radiation citizen science collection project. The question is, who was in those areas of no data for that project? Was it humans without technology, crops, forest, wetland? Do you have ideas about what was there?
Yeah, so for most of those areas that didn't have data, it was mostly forested, and some of it was semi-mountainous. It was like right on the edge of the mountains. And a lot of those areas are considered of great religious significance to people of Japan. So it doesn't mean that they are not also going into those spaces, but they don't necessarily live there. But yes, a lot of those areas do have, let's say, sparse movement of people within them.
Great. Another question here is, do you think crowdsourcing could help revolutionize ground truthing?
I think for sure, and I think it already has in a lot of capacities. I see it in so many ways as revolutionizing also machine learning and AI inputs, checking on things. So I've been involved some with a project where they're having using Google Street View combined with remote sensing imagery, and then an app on the ground where people are confirming locations in person. So you could have a task, let's say, to go to a specific area. There's also some of those for land cover now, where people go to a specific area, let's say in the middle of Kansas, and they mark that this is actually a cornfield. And so these kind of projects are definitely starting up, and I think will reshape how we do ground truthing, and already are starting to.
All right, we got several more here from Dan Dugas. Do you think that spatial factors are embedded into the spatial data by the local nature of crowd knowledge and data? They're more familiar with the area in terms of its norms versus its extremes.
Yeah, I think for sure that there is like an embedded knowledge of what's important and also what areas people are interested in. It really depends on the type of task that you're asking. So I think if you're crowdsourcing, in this case, let's say for radiation or for flooding, it's not a particularly developed task in and of itself. It's you might carry a sensor through that area, and you don't really have to have a specific knowledge to contribute to that project just by carrying the device. Other projects might have more of an input that you need to give. And so I think there are specific factors that can influence that knowledge and people's familiarity with it. Let's say taking a picture when there's bad air quality and contributing that for air quality because they recognize that air quality is different versus having a sensor that's just always there and monitoring air quality. So I think in those cases, you do need some local knowledge of what the norm is and the extreme. And these projects can help to bring that baseline to get an idea of what's normal so that you can actually show what's different and what's, extreme.
Great. Here's another one from Shigong. For the flooding project, how big are the data quantities for the crowdsourcing image data, and what method do you use to identify the depth measurement from the images?
Yeah, so I think there are about 500 images that we had that were specifically from that event or contributed to that event. And it was just algorithmic based thing that was based originally off some based off people originally doing the measurements, and then through an automated process of the rest of the images of the depth in comparison to other physical features. So you could look in relationship to, let's say, a bridge or to normal height on a house. You kind of get a framing of where the ground would be based on other features, and then do a measurement in relationship to that. So it does take some geometric, frame of reference in order to get an automated calculation of depth.
All right. From Bo Romero, a question about how you might model citizen science observations. For example, the same amount of water might pose different levels of risk in different places, and different people might have different perceptions of risk or different perceptions of quantities of water.
Yeah, and I think that goes back to this question of what specifically the task is. So is the task to say if the flood is risky, or is the task to just take a picture of the flood depth and maybe input how deep you think it is? And so these are different types of tasks. One is based off of perception. So let's say I have a observation, let's say there's social media and someone says, this is the worst flood ever, right? It's probably not the worst flood, but even if it was, it doesn't tell you how deep it is or how bad it is in that place. And so I feel like the citizen science approach can try to get at more precise scientific questions about flooding or about these topics. And if we're looking at perceptions of risk, that's another aspect. That's something else that we could ask, kind of like as a research question. But it's, to date, something I haven't done, as the perception of how much risk that causes to you. But I think it's meaningful in and of itself, and it can be asked, and it probably is in some capacities. I'm sure there's some projects that do ask about that perception.
Thanks. All right. Question about the flooding project from Rold. Could citizen scientists submit GPS points of just the shorelines, in quotes, or the maximum height of the floodwaters so that they aren't going into the water at all? Would that be a way of preventing them putting themselves in danger?
Yes, that is the goal. Like, that is what they're never asked to do that. And they're supposed to just submit the edges of it. And you can provide certain guidelines for that of what you should take a picture of. But you always have certain people that might, you know, do something that's not the most brilliant thing to do. So that's more of a concern that someone might take it to that level, as opposed to not providing that guidance. Like, so I think it's about how you frame the guidance and making sure that it's in a certain way so that people know what they're supposed to do and not supposed to do.
Yeah, I was wondering myself, I was thinking about whether there's an analog with the storm chasers, you know, who are going out and doing atmospheric measurements around tornadoes and photography. I mean, is this the same case, or is that a more trained personnel?
Yeah, I mean, I think this is the same type of concern. Like, it's not that I have evidence, let's say, of this concern, but I think it's something we do need to think about, and it's something about how you frame it and frame the question and ensure that you're not encouraging people to do more hazardous, you know, efforts, let's say.
All right. A question related to that about how people are impacted from Brad Hansen. Is it always good to have real-time data? What are some of the cons? What actions flow from this ability? And what are the effects of those actions?
Yeah, I mean, so real-time data could allow you to actually take actions, right, within that time frame. But those actions are based off of what you have at that time, the data that you have available at that time, which, if it's not accurate, can pose problems, particularly if it's intended to misguide you. And this is part of like what I almost think of like really frames within this geospatial intelligence kind of realm, which is used to dealing with deception or these kind of aspects that you have to evaluate it in some other way. And this is where this role of validation comes in, where you should compare it and see if it actually makes sense. You could look at the flood model and compare it to something and see, okay, well, they say it's flooded there. Do I see an avenue by which it could actually be flooded? You have to actually think about these questions as opposed to just assume that the data is right in real time. And so I think it's a really meaningful thing to look at. And there's actually some really interesting work with that related to earthquakes, where there was a case in Haiti where someone from Texas was saying that there was an orphanage that had been damaged, and it hadn't. It was just some random person who was trying to cause trouble. And so you have to be aware that there might be other inputs. And one way to do that is to look at the individuals that are contributing, to look at, let's say, if somebody contributes multiple places in the same place, look at their location of where they are posting, and not just assume that everybody is a good actor. And that's unfortunately the world that we live in.
I'm going to jump ahead to a question by Bo, which follows on that. Is just, you know, could you talk about the concerns and opportunities of anomalous observations, or observations with little additional support?
Yeah, and there are some concerns there of these anomalies, and one way to approach that is to compare other data that's collected in the same place, and even within the same data set. So I talked about this some with the SafeCast data set, or the SafeCast group, as instead of, if you have an anomalous observation, just adding it to the data set, which might show like a peak suddenly on the map and get people worried, to compare it to, let's say, if you have another sensor that's in the same space, and see if you can kind of collaborate or kind of, you know, confirm that observation. Or maybe there's a sensor that's gone bad, that's not collecting properly and needs to be recalibrated or something like that. It could help to identify some of these anomalies and allow you to kind of curate that data set to show things appropriately. And there's a lot of work there with anomaly detection that needs to be done, even outside of our typical traditional statistical modeling of relationships, but also in this new space of crowdsourced observations that are coming in at different velocities. And it really presents a different sort of picture than traditional anomaly detection.
So a question about how you use this data to interact with decision makers from Leo, saying, after we finish using multiple models and data sources, how should we aggregate those results? For example, in your projects, you have multiple outputs based on sensors, models, crowdsources, and other sources. Should we show those results separately? Should we aggregate them into one final figure or map? Which is the best way if we want to report to decision makers?
Yeah, and I think this is a really important question, and it can be case specific. So it can depend maybe on what you're trying to display. And I've worked with this, I didn't show it, but I've worked with the sum of aggregating or combining the different sources and showing different levels of uncertainty. So using a Bayesian approach, and you can weight, let's say, the modeled results differently depending on the source it comes from. Let's say the user or the individual that's contributing, the sensor that they've been using, that it's been used multiple times and seems to be valid in other places. And you can try to weight the results. And I think that can be a really useful way of framing this, and also showing something like that graduated uncertainty levels, where you're saying, well, we're certain that it's a high level radiation, we're certain it's a low level radiation. It's somewhere between, let's say, 400 and 600 according to all observations. That's like can be a very powerful final message that you give to decision makers of, it's at least this high, everyone agrees, as opposed to all the fluctuations here and there. A final output where you just succinctly say above this threshold, I think can be really useful.
Another question about that project, as to whether you use soil samples to compare with air samples in the areas with the most radioactive levels.
Yeah, so I didn't specifically work with soil samples for comparison. I did use the concentrations data set, the deposition data set that the JAEA provided. And that is looking at the ratio between 134 and 137 in these environments. And that's what I use to decay the radiation levels, because depending on which one of those is present, you have a different decay rate. And so that was necessary in order for me to have an appropriate decay function. And it was able to be checked and show that it does decay to the right timeframes and future steps of observations that were at that specific time. And this kind of thing from the soil can be helpful for that. There's a lot of work that is being done in the soil sample side of things, particularly as soil changes. Let's say they have really heavy rainfall in that area, there can be new releases of radiation from that soil, and it can, there's been some projects that have looked at the flow of that temporally through streams and potentially into water supplies. And so that is definitely an important thing, and I haven't looked at it enough, but I think it's another important factor that's a different type of distribution than just the air samples that I was looking at.
Great, thank you. We just threw a bunch of questions at you and you're just like knocking them off. So does anyone else have any other questions? I don't see anything else in the chat. Final comments?
Verbally is okay too.
Well, I'll just say thank you for being with us and presenting this fascinating research. And I know a couple people got to talk with Carolynne earlier in the day, but she's also happy to take emails for people who want to follow up and learn more or engage more. Any final thoughts, Duval?
Could you give us like a very, I'm teaching a course on coronavirus right now on the pandemic. Could you
Yeah.
give like a minute-long summary of that paper that I mentioned that you guys have forthcoming?
Yeah, absolutely. I think the revisions just went in last week, so it should be out very soon and I can send it to you. So the main conceptualization of the paper was to tie between air quality that we observe from both ground air sensors, remote sensing of air pollution, and with mobility indices. So I really was pulled in because of the mobility indices and this integration between the projects. And looking at mobility using the Descartes Labs indices, which is based off of smartphone use. And so we're basically able to see areas where people are not moving as much, not traveling as much, very strongly relates to improved air quality. Except it doesn't so much for PM 2.5, which we looked at as more of a constant and is not as influenced just by people's driving and sort of behaviors. We still have diesel trucks. We still have a lot of other things that are contributing PM 2.5. So it really kind of tries to bring together a couple different data sets to look at changes in air quality from March, April, and May. I think we really focused in on April, which was like the most intense time period of lockdown, and compare it over the last 5 years of data to see changes that we have this year in air quality.
Well, that's great. Thanks, Carolynne.
Yeah, absolutely.
All right, well, thank you again. I'll remind everybody that our next presentation in the series is 2 weeks from today on October 30th, and that one will be hosted by the folks at NMSU, my colleague Chris Brown at the helm. And so we will convene then and see you all in 2 weeks.